Hello, everyone. Welcome to the London Machine Learning Meetup. My name's Aaron, and I'll be your host for the evening. So, yeah, today we've got a really exciting talk by Ali Behrouz from Cornell University. And yeah, I just wanted to quickly go over the format for today's session. So today we're going to start with a 40-minute presentation by Ali. And this will be followed by a 20-minute Q&A session, which will be moderated by Jiquiz Wang from the University of Illinois, Urbana-Champaign. So if you have any questions throughout the presentation, please feel free to use the Q&A tool. And yeah, any questions that you guys put in there will be answered at the end during the Q&A session. So yeah, thank you everyone for joining, and I'll hand it over to you, Ollie.
Thank you very much. Can you see my screen?
Yeah, we can see your screen.
Hello, everyone. So, yeah, I'm going to talk about our latest work on Titans layering to memorize at this time. Yeah. So I'm going to start the talk by talking about the different perspectives that can help us to design deep learning architectures. And actually, I really think that having different perspectives is very important because there is a one single mathematical formulation and there are different interpretations for a single mathematical formulation. And all of them will lead to a specific architecture, but actually the perspective of the way that we look at the problem is very important to understand how do we want to improve this specific architecture, improve a next generation of architectures and so on and so forth. So I will review some of the important perspectives in the past years. So basically traditional architectures like LSTM, GRU, and nonlinear RNNs are all based on this memory perspective. And it says that basically the model is based on one assumption that says memory is a neural update caused by an input. And then we define the learning process as a process of acquiring effective and useful memory. So basically that's how we want to design our deep learning architecture. And so if we want to somehow get inspired from human brain, one thing that we can see is that we have something like long-term and short-term memory. So basically we have similar patterns in LSTM. And also there's a forget gate that help us to manage the memory. So again, in LSTM, we have these forget gates and so on and so forth. Then we go to these attention or transformer era that basically most of the focus is on efficiency, how we can effectively design architectures that can utilize the matrix multiplication capacity of modern accelerators like GPUs, TPUs, and all these things. And actually, that perspective is is going well until now. And concurrently, we can see that there are some other perspectives that help this efficiency era. For example, we can see that 2018 or for example 2020, there is a dynamical system perspective that we see. For example, the sequence as a dynamical system, and we want to use linear approximation to model this dynamical system. And actually we can see that linear approximation can be surprisingly effective. We can learn something about convolutional form of these architectures, and for example how we can efficiently implement them. We can see a generalization of the forget gate that we have seen in the traditional RNN, which they called it discretization. And actually, there are different micro changes in the architectures that all of them comes from this perspective. And one thing that I really believe in is that now we need to have the modern memory perspective goes to the like new perspective that can help us to design more powerful architectures. And that's the part that help us to design Pythons. So basically, before going into the details of what these perspectives, I mean, how this perspective can help us, I need to explain why this perspective is important and why do we want to like get inspired from human brain and like have this memory perspective. Basically, human brain has evolved for more than millions of years. So basically, it's very effective, very efficient. We can learn from a few number of samples, and so basically everything is like great. So that's a great source of inspiration. We can get inspired from brain and like design a very powerful neural architectures. And some people might say that there are a lot of things that we can do, I mean, sorry, AI can do, but we cannot do. For example, you might have even not AI, just machines. For example, you might have a calculator that can calculate like fast multiplications and all these kind of things, but we cannot do that. And actually, if we think about that, we can see that all of them are some biological restraints. We are like slow in some operations because there are some biological restraints that those are not actually architectural restraints. So the architecture and how the brain is like learning could be a great source of inspiration for us. And again, this process would be based on these two assumptions that I mentioned. Memory is a neural update and learning is a process of acquiring effective and useful memory. So given this perspective, this memory perspective, when we want to like get inspired from human brain, what are we missing in current architectures? So the first thing is that neural networks needs to constantly learn and memorize. So basically there is no like pre-training and then goes to the post-training and something like that. We are always learning. And actually, we have some persistent long-term memories, but we do not have infinite context. And what does that mean? We can remember some information from like 20 years ago, very old time, or we might remember something from that time. But actually, we do not have all the information over the past 20 years. And we forgot some information, because our memory is limited. And actually, we need to have a good memory management to learn what information is worth remembering and what information should we just forget and all these kind of things. So basically, I really think that instead of thinking about how we can have infinite context, we need to think about how we can have persistent long-term memories. And another like intuition from this memory perspective is that look at our short-term memory. We can see that our short-term memory is very accurate. And what does that mean? It means that, if we got some information in just like 30 seconds ago, we cannot hallucinate about that. Everything is very clear in our mind. We have all the information, and actually it's very accurate, very similar to how attention works. In attention, we have like all the pairwise interactions between all the tokens, and actually that's very accurate way to model all the dependencies of the like tokens in the context window that we have. And then if we look at our long-term memories, we can see that we might hallucinate about some of the details, we might hallucinate about what has happened in the past. And so basically all of them are fading memories. And that's because our long-term memory is like constant or fixed size memory. And we need to have a good memory management to handle incoming data. And so it can help us to like have long-term memories, but with the cost of forgetting some of the information. So that's very similar to how recurrent neural networks work. And so basically, in this way, in this like Titans work, our main intuition is that we need to use attention as a short-term memory of the architecture, and then use a long-term memory. Recurrent networks as a long-term memory. And the question is how we can like design that long-term memory in the way that it's going to be effective at test time. And finally, another thing that we are missing in current architectures is that our memory is a neural architecture. It's not a simple set of neurons. And what does that mean? And let's look at the traditional RNN or even modern linear RNNs. And basically, what's going on here is that the data comes, we project the data into the hidden space, and we have a memory, or usually it's called hidden state in the literature. We also project the hidden state or memory, and then we just like add these two together to update the memory, and we just repeat this process again and again every time that we want to like update our memory. Also, we have the retrieval part in the sense that anytime that we want to like get something from our memory, we just like multiply our memory by a matrix to get the corresponding data. So that's also the retrieval part of the recurrent neural networks. So given this perspective, the question is, are we really like making progress over time? So for example, let's look at the RedNet architecture in 2023, and we can see that if we mathematically formulate this process, we will get this like closed form recurrent formula for RedNet. And then 1 year later, we have like Mamba 2 architecture, and if we just like compare these two, we can see that everything is the same. The only thing that is changed here is just we have made this parameter data dependent. So we can see that we are not making fundamental changes to the architecture, but we are like making we are changing some details to help the model manage the memory better. Now let's look at like linear transformers. And what does linear transformer mean? We just replace the softmax by a separable kernel. So basically, when we have something like QTKI, the dot product of QTKI, we can just like separate them and apply the kernel on top of each of them. So basically, this formulation of the output of attention can be simplified to this formulation that we have here. So if we look at this summation here, we can see that this summation is very similar to the memory of this transformer, because we are storing the keys and values into this memory. So basically, the interesting part is that this memory part can be written as a recurrent formula, because it's a summation. And if we define that as empty, we can see that empty can be calculated as empty minus 1 plus the new incoming pairs of keys and values. So basically, there's a recurrent formula for a linear transformer as well. So if we look at, again, the high-level process of linear transformer, we can see that everything is the same. The data comes, we project the data, there's a memory, we project the memory, we just add these two to update memory, and the retrieval part is exactly the same. But the only change here, the only fundamental change that we can see here is this memory architecture that we have. Basically, instead of a vector, now we have a matrix value memory. So it can help us to better manage the memory and have like more powerful memory architecture. So it can help us to have a better deep learning architecture. So the idea here is that we can just like extend this idea. The first part was the vector valued memory, and then we go to the matrix valued memory. And so basically, why not? We can have for example, neural networks memory, and that's also discussed with the like test time training paper TTT. So the idea is that the data comes, and we want to like store all the historical information into the parameters of our neural memory module. And so basically, the storing part to the memory can be something like the training of the neural memory. And the retrieval part would be just a simple forward pass. We just send the query to the memory and ask it to like reply with the corresponding information into that specific query that we have. So basically, the memory part would be just a neural architecture. The memory is, I mean, storing the memory would be just the training of the neural architecture. And so that's the idea. But the question is, what information is worth remembering, and what should be like remember at test time? So the simple idea here would be just saying that we can just train this neural network based on the gradient of the incoming data with respect to the current state of the memory. And what does that mean? It's very similar to the surprise metric, because human usually remember something that is very surprising and can somehow violate their expectation. So the one way that we can interpret this formulation is to say that this gradient is like calculating the surprise metric. And so it says that how much xt is different from the previous data samples that mt has seen so far. So basically, if xt is like very different from the previous data, we can see a very large values for the gradient. And if like it's very similar to other data, and like the previous pattern can fit all the data that we have, then this gradient would be very slow. So basically, this gradient here is like modeling the surprise metric. So that's one way to interpret that. And basically, based on the surprise, we can say that if the surprise is a lot, we need to like memorize that. If the surprise is like a small value, then we don't need to like memorize that, and we can update or train our neural memory based on this simple formula. However, the main issue here is that let's say that we have one specific token, and this token is very surprising to us, but because this token inject a huge surprise to the memory module, then its consecutive tokens are not surprising anymore. So basically, we might just ignore consecutive tokens. But the fact here is, all those tokens are important to understand the context, and we cannot just simply, ignore all those tokens. So our idea here was to like break this surprise metric into two parts. The first part is the past surprise, and another one is the momentary surprise. The momentary surprise captures the surprise by this specific incoming data sample like xt. So basically, the momentary surprise would be just a simple gradient, as I mentioned in the previous part. And then we have like this past surprise that is the state for like see how much previous tokens was surprising to us. And actually it's decaying over time, because assume that, for example, we have one very surprising token, and like 1 million tokens later, we don't want to like see the effect of that specific token, because we just that token is just passed. So we have this decay mechanism that control whether we want to like have these specific past surprise, or we just want to like ignore that. And one important question here is that everything that we are building is based on this gradient part, and we are saying that anything that is surprising to us should be like memorized, and any other things should be just like should be forgotten here. And one might say that, let's say we have some noise in the data, and actually it's very surprising. What would happen is like, is this neural memory very sensitive to the noise? And the interesting part is like this theta t here. Let's say that we have a very large surprise. So the data is very surprising to us, but we don't know whether like this surprising context is important to the entire context, or it's just something like outlier or noise or something like that. So basically, this theta t is an input dependent parameter that can handle those cases. If the surprise is large, but the context is irrelevant, this theta t would be very close to 0. So we just like ignore these incoming data and go with the previous state of the memory. And if it's not, then this theta t can be also a large number to emphasize that we need to memorize and memorize this specific token and so on and so forth. So basically that's the main idea here. But as I mentioned, we have extended this, from a vector. We have extended the memory architecture from a vector to a matrix and then to the neural architecture. But still, our neural memory is a fixed size memory. So we need to somehow design a memory management that is powerful enough to understand what information should we just focus on and what information should be forgotten. So another important question here is what to forget at test time. So basically the idea is simple for forget gate mechanism that we are using here. Basically we multiply the previous state of the memory but by 1 minus alpha t. So when alpha t is close to 0, then it means that the context is relevant and we don't want to like remove the past memory. We need all the past information. So basically we don't want to like remove anything from our memory, and basically that's what's happening when alpha t is close to 0. And when alpha t is close to 1, we can say that we are raising the entire memory because probably the context is changed, or this specific token is not very important. I mean, the past historical information is not very important for this specific token, and so on and so forth. So basically this forget mechanism is like implemented by this simple multiplication by 1 minus alpha t. Now, until now, we have seen that how we can design this long-term neural memory that somehow has a very powerful memory management. But if we want to like scale this neural memory, we might face so many like issues about how we can like make the training more efficient and so on and so forth. So the question is how we can like parallelize this process that we are presenting here. And if you look at like the recurrent formula that we have here, we can see that MT depends on its previous state in two parts. Like one is here and another one is inside the gradient. So basically, we cannot use any specific associative operation here and use like parallel scan algorithms and all these kind of things because this process is not parallelizable. However, one thing that we do here is to somehow like model the approximation of this process and replace this gradient with the gradient with respect to the previous state of the memory in the last chunk. So let me go into more details. Let's say that we have one specific sequence, and what we do is to chunk this sequence into some subsequences. So basically, when we are like calculating the gradient in these like green chunk or green subsequence, one thing that we are doing is to calculate the gradient with respect to the last state of the memory in the previous chunk. So at the beginning of like this subsequence, the computation for this subsequence, we can calculate all the gradients at the same time in parallel. So that help us to like have a linear recurrent formula. How? Let's just call this gradient UT. We can calculate all UTs at the same time. So basically we have all UTs in this specific subsequence. And if we look at this surprise metric formula that we have, we just like substitute this gradient with UT, and we know that UT is like given because we have calculated at the beginning of this chunk. So this formula is linear recurrent formula, and we can just like simply parallelize it inside each chunk or subsequence. Basically, inside each chunk, the recurrent formula would be something like linear recurrence and parallelizable. And like between chunks, we are doing some nonlinearity. So basically the recurrent formula there would be something like nonlinear recurrence. That's how we parallelize the process. But the main issue is that if you want to like take advantage of TPUs and GPUs, we need more matrix multiplication in the training. And basically we build up in the work on the test time training that I mentioned. Basically, the interesting part here is that we can somehow expand this recurrent formula and write it as a matrix multiplication. You know, MT is MT can be calculated as 1 minus alpha t times MT minus 1. And this MT minus 1 can also be written as 1 minus alpha t minus 1 MT minus 2, and so on and so forth. So basically, we can just expand this recurrent formula. And if we do that, we need this initial state. So basically we have beta t m0, and beta t basically is just the multiplication of 1 minus alpha j from 1 to t. And so basically we have beta t m0 minus this summation that we have here. And so basically the calculation of the first part is very simple, and also it's just a simple multiplication. So we just need to like write this summation here as a like matrix multiplication format. Now, just for the sake of simplicity, let's assume that MT is just a linear function. It can simply be extended to any form of neural architecture, but just for now, assume that like MT is just a matrix. And in that case, this gradient, because, you know, this gradient part is like the gradient of this loss function, and this loss function is basically just the MSE loss. We have like keys and values, and the memory want to like map keys to the values. So basically the loss function would be W0 times K minus V. And we just take the square norm of this one. So that's the definition of the loss function that we have. So if we just replace MT with the matrix and take the gradient, we can see that the gradient would be very simple, and basically just this function that we have, W0 times KT minus VT times XT. And now if we just like substitute this term that we have here into this summation, we can see that like these theta I, beta t, beta I are basically some scalar values. So one thing that we can do is to construct a matrix like theta b here. And so theta b is a diagonal matrix such that its diagonal elements are theta i's. And similarly for b, is a diagonal matrix such that its diagonal elements are beta t over beta I. So basically, this matrix multiplication would be the Hadamard matrix multiplication, because, you know, both of them are diagonal, and it can model this term that we have here, theta I times beta t over beta I. And then, you know, this gradient that we have here can simply be calculated using this matrix multiplication, because, you know, W0 is just like W0, and then we have like this K here such that its rows are KT, and then we have like this V, which is the matrix form of this VT, and basically here XT would be matrix X, which is our input. So all these terms can be like calculated using matrix multiplication, and this summation would be equal to this term that we have here. And you know, this term is basically only based on matrix multiplication, and so it's like parallelizable, and also very efficient on like modern accelerators like TPUs and GPUs. So until now, we have seen that how we can design this neural memory, how we can like train it in a parallelizable manner and in a fast and efficient manner. And now the question is how we can incorporate long-term and short-term memory. Until now, we have designed the long-term, and our intuition was attention should be the short-term memory part, and how these two should be connected. Even in the neuroscience literature, it's not very clear that how these things are interconnected, how we are like passing information from short term to long term, and so on and so forth. We don't have any specific thing to get inspired by. We have like three different ways of incorporating long-term and short-term memory, and each of them has its own interpretation. So I'm going to start with the memory as a context. So in the memory as a context, the main intuition is that our long-term and short-term memory are two interconnected systems, and each of them are helping the other one to like better perform for the downstream task that we have. So the idea here is that the data comes and we pass it to the long-term memory. We retrieve relevant information from the long-term memory and then concatenate it to the sequence that we have and then pass it to the attention. Now, attention as a short-term memory has the information of the current context, the incoming data, and also the past information, only the corresponding part of the past information from the long-term memory. And basically, it has the ability to somehow understand which information is important here, and it needs to like focus more on the current context or focus more on the historical data that we have. And so it's like have more flexibility and it's more expressive. So in this step of this architecture, this is the long-term memory that is helping the attention or the short-term memory. Now, attention can focus on different part of the context, so understand which part of the context is important. So now, this is the attention that is helping the neural memory, and we pass the output of the attention to the neural memory to update its values. And so basically, now attention is helping the long-term memory to understand what information is important and what information is not. So it helps to have a better memory management. And finally, we just like combine the output of the neural memory and attention. So we have like an architecture that both of these two branches of memory are interconnected and are helping each other. Now we go to the like next one. We have memory as a gate. So basically the idea here is that, long-term and short-term memory are not interconnected. And basically they are just two different branches of memory. The data goes to the attention and also goes to the neural memory. And, the output would be just combined together to get the final output. So that's the main idea behind this memory as a gate. And finally, we have this memory as a layer, which is a very common architecture in the literature. Usually when we have an RNN and when we want to like design a hybrid approach, we just put RNNs and attention in a sequential manner. So that's a very common approach. Basically, the idea here is that the data goes to the long-term memory, and then the output of the long-term memory goes to the attention, and we just like repeat this process across the depths of the architecture. And so the final output would be the output of the entire architecture. So basically, yeah, we have seen that how we can design this long-term memory, how we can train it in an efficient manner, and then like how we can combine it with the attention. So the attention like be the short-term memory, and then the long-term memory plays as the long-term memory. And now in this part, we want to see that how we can how it performs in like downstream tasks. And one thing that we can see here in the first task, which is the language modeling and common sense reasoning, we can see that like our long-term memory without any attention can outperform all the baselines, including hybrid versions. So basically, this long-term memory is very effective, and it can outperform both all three types of attention-based or transformer, linear RNN, and also the hybrid version. without like any additional attention module in the architecture. And also when we add additional, attention module and have like MAC architecture, MAG architecture, or memory as a layer, then we can see that we can see some improvements over the pure long-term memory module. And the interesting part is that, this memory as a context and memory as a gate that we discussed are much more powerful than this common approach in the literature that is memory as a layer. And so that's also a very interesting part because it's worth trying to like design like future hybrid architectures in the format of like memory as a context or memory as a gate, and they might be like more powerful than memory as a layer. We can see also similar results or the same pattern in the smaller scale as well. And another experiment that we have is the language modeling. So basically, the needle-in-haystack state tracking or the Babylon benchmark. And here we want to like somehow show that our architecture can scale to very long sequences, and it's very effective in that manner. So this task is like basically a needle-in-haystack task. So there's a very long sequence, and we just hide some facts in between some tokens, and then we ask a question. So basically the model needs to find all those facts and then reason about the final output. So that's the main thing here. And we can see that like Python's in the format of memory as a context is very effective in long sequences, and it can achieve like more than 90% in sequences with the lengths of 1 million and 2 millions. And also when we scale it to 10 millions, we can have a performance better than like most of the models, and also better than 70% accuracy. And we do not see a huge drop that we can see in like other like baselines or like ultra large models like GPT-4, GPT-4 Omni, and all these kind of things. And so one thing that I need to like emphasize here is that for these specific long range experiments, architecture matters a lot. So basically, if we just focus on a pure long-term memory, or for example, MAG architecture, we do not see this pattern, and it might not scale to like 1 million tokens. So here we can see that the architecture matters a lot. How do we want to like combine short-term and long-term memory? And we can see that having an interconnected system of short-term and long-term memory is very important for long-range tasks. And also another thing that I need to like emphasize here is that fine-tuning is very important. And so basically all these linear recurrent models like Mamba or RMT and Titans are fine-tuned, and it can like improve the performance. Finally, we have this ablation study. And basically, one interesting pattern that we can see here is that there is no free lunch theorem, and there is no specific like type of architecture that outperform all others in all different kind of tasks. So for example, in MAC architecture, we can see that we have better results in reasoning and long context. But for the language modeling, MAC is better than MAC architecture. So the interesting part is that both of them are performing better than the memory as a layer that I mentioned, is a very common type of architecture to design hybrid approaches. And also like this momentum part is the path surprise metric that I mentioned. We can see that it's very important for a long context task. And so basically, if we just remove it, we can see a very huge drop in the performance. That's pretty much my talk. And actually, we are actively working on efficient and effective architectures. And if you're interested in these kind of research approaches, you can reach out to us. Thank you very much.
Amazing. Thank you for that really insightful talk, Ali. So yeah, now we can move over to the Q&A session, and this will be moderated by Jikri. As I mentioned at the beginning, please use the Q&A functionality on Zoom. And if you would like to ask, your question out loud, please raise your hand, and then, one of us can unmute you and allow you to ask your question. So yeah, over to you, Shikri, for Q&A
Right.
session.
Yeah, thank you, Aaron, and thanks, Ali, for the really fascinating presentations. I think I will start with some like the audience questions, and then I also have some questions myself. So the Renai asks that the slide on the 3 different evolving perspectives on the memory is very interesting. And will you share the slides, and are there some references to publications to read up on this? Thanks. Yeah.
Do you mean like these 3 variants of the perspective?
Yeah. I think this is the
Yeah. Unfortunately, I think there is no, for example, I mean, to the best of my knowledge, there is no survey that like discuss deep learning architectures in this way. But for this specific like modern memory perspective, we have an incoming paper this week probably that might discuss some of the details that how we can like design neural architectures based on this memory perspective.
Okay, cool. Yeah, I think I think this is really pretty interesting because I previously do not really have much knowledge on this, but when I see these perspectives, I think it's really a fascinating angle to understand how our architecture evolves. I also have some my own questions, follow-up questions, like when I listen to your talk, I think like you mentioned there are some gradient updates to organize the memories. So I'm just thinking about if like the multi-step gradient descent will cause a better performance. Well, we know they will cause some efficiency issues, but will this make things different, make the performance better here?
Sorry, I might miss something. Do you mean, so just to make sure that I understand the question correctly, do you mean like using gradient descent
Yeah,
for?
like multiple steps of gradient descent to ensure maybe it reach better optimalities.
I see, I see, I see. So basically, we can have like multiple steps. Do you mean like multiple steps of gradient for each token?
Mm-hmm.
Yes.
I,
So yeah,
please go ahead.
yeah. I think that's a very interesting question, and yeah, I think basically it really depends on the data that we have. For example, if we want to do something about, for example, computer vision and something like that, we usually train our neural memory uh, with like repeating the data, and we go over the data several times. And I don't have a very like mathematical formulation or a very very rigorous like reason for that. I'm just like talking about my intuition. Is that the distribution of data in that case, or in those kind of like data set that we have, requires something like multiple gradient updates per each sample, so we could like learn different kind of patterns, or in another sense, the data is very complex, so the architecture cannot simply learn from data in one pass. But my guess is that for language, it might be enough for like do one pass. But actually, there is a very interesting paper recently. It's called Delta Product, and so the way that they are like doing is to do multiple gradient descent per token. And they have shown that it can achieve better results than a pure like gradient descent. And however, if you want to like do 2 steps of gradient descent, then the efficiency will drop. And there's a trade-off between efficiency and effectiveness. And depend on the like application that we want to do, we need to like find that sweet spot that it's very uh, effective for the task that we have.
Yeah, thanks. I think the answers is pretty like answer my questions. I think maybe I will just treat this as some kind of like test time scaling methods for your framework. Yeah, I actually have a follow-up questions on this. Is about I think later you mentioned about we need to chunk the sequences to make the training in a parallel manners. So like in practice, like how can we determine what the chunk size would be, and will the different chunk size be a matter of the performances and efficiencies?
Yeah, one thing that we are doing here after chunking the sequence is this approximation part. Basically, we replace the gradient with the gradient with respect to the last state of memory in the previous chunk. So that's a heuristic approach. And basically, if we choose the length of the chunk size very small, then we have more accurate heuristic approach. And if we just increase it, then we are like have a lower accuracy heuristic in that manner. There's a trade-off between, again, there's a trade-off between efficiency and effectiveness. If we choose, for example, chunk size equals to 1, then we have a pure recurrent architecture. It's very slow, maybe like 6 or 7 times slower than what we have. But if we choose also that chunk size equals to 256, then probably we might not get a very good results. So basically there's a trade-off, and in the paper we usually use a 16 as the chunk size.
Oh, I see. Cool. Yeah, I think it's pretty reasonable. I think I have one also about the high level questions about like want to hear about your opinions on like what the future architectures of the models would be like. Is it like a combination of the attention, like a short-term memory plus like these kind of long-term memories modules, or do you think it will be some other possible architectures?
Yeah, I think based on this term that I mentioned here, that our short-term memory is very accurate, and then our long-term memory is something like a fading memory. I really believe that we need to have a hybrid approach of this short-term and long-term memory. But we might find some alternative architectures of attention that are actually accurate, but they are not the attentions that we know right now. But I think we really need the hybrid approach of short-term and long-term memory, something that can handle like very accurate dependencies of all tokens in the current context, and something else that can handle the long-term memories similar to RNN. So yeah, my personal opinion is that we need to have hybrid approaches of RNN and attention, and probably we need to like somehow separate our uh, research directions. One direction into designing more effective long-term memories or RNNs, and another research direction goes to like sparsifying attention, or for example designing more an effective attention paradigms and all these kind of things. So yeah, that's generally my intuition about that.
Yeah, cool. Yeah, I think yeah, I think that's pretty insightful. I think I have actually I kind of like some similar opinions to yours. I think in my mind I also have one last questions about this about your talk is like when you do the experiments, like maybe doing these kind of maybe the test time training may cost more time. Will this be comparable to the the quadratic complexity in the attentions?
Unfortunately, I don't have the plot here in these slides, but we have a plot in the paper that compares the training time of like these test time training or Titans with the transformers and also other recurrent architectures. And when we have something like very small context window like 1K or 2K, we can see that attention is very efficient because most of the hardwares that we have are actually designed for efficient matrix multiplication, and attention is like pure matrix multiplication. So that's the reason attention is very effective. But when we increase the context lengths to, for example, 16K or for example 8K, we can see that the attention is like the attention performance is like dropping. By performance, I mean efficiency. There is dropping, and so basically, if you want to like have a very long context modeling, we need to somehow use these kind of architectures because all of them are more efficient than transformers. And compared to other like architectures, Titans are faster than models like Mamba. But also there are some like modifications like Mamba 2 or some specialized kernels like Triton kernels and these approaches that might help to improve the performance, but we do not have a specialized kernel. I mean, in the experiments, we do not have a specialized kernel for Titans, and it's just a simple Jackson PyTorch code. So also, I think it's a very like interesting results because without like any specific optimization of the kernels, we can get a very efficient model that performs well on long context.
Yeah, cool. I think thanks for your answer. I think Aaron, do you have anything to add here?
Yeah, so in terms of questions, I think you've basically covered everything. If anyone else in the chat would like to post any further questions for Ali, feel free to use the Q&A. So we can wait a few minutes to see if any other questions are coming in.
Yeah, just please use the QA so we can see and select what if you have any. Just a quick, small things. Will we share the slides or the recording somewhere else so that
So we can send the slides out, provided you're okay with that, Ali. And on top of that as well, this meeting is being recorded, guys. So if you are interested in watching this meeting or any other previous London machine learning meetup sessions, you can find it on our YouTube channel. So if you guys feel free to subscribe, and you'll see when the next video is being uploaded as well. So we haven't had any questions for now. So I think now could be a good time to wrap things up. I just wanted to say, yeah, thanks so much for the great talk, Ali. And also thank you, Shikri, for hosting or handling the Q&A session. I also wanted to thank Evolution AI for sponsoring this event. And yeah, thanks again for the great talk, and I hope you all have a great evening.
right? Thank you, everyone.
Bye, guys.